playback of Mathematic 2. The game actually got to name them. Big Bute is a Highland cleric that we found in the game. It's a good name. And, the fact that he has 69 hit points is a coincidence, but it's still a pretty funny coincidence. We've entered the code. Because of your superior intellect and intelligence, you have saved Kron and all of its warrants. This ship, created by the ancients, is a grand experiment designed to populate this distant world. Prepare to beam down in Might and Magic 3. It's here, on the floor. I didn't see it. Thank you, my friends. You have banished chaos and rejected the false path of uncompromising order. Under the weight of the evidence and from the skilled pressure tactics of your lawyer, Lucas breaks down and admits to their crime. Congratulations, Ace. I think we're having a real moment here. I've changed my mind. I can't give her up. You can have your money back. How could I sell something so dear? Then again, a deal's a deal, right? Right? Catch you later. Good luck. Enjoy. I'm out of here. Let's pick up the bottle of grog here. Pick up the root beer. Use the root beer with the jug. Apparently root beer works very well. We get to see an instant replay. And a view from the blimp as well. I wonder what would happen if I tore the leg off this thing. Ark.
You have a resume. Madre de Dios, es el cuello diablo. Come on, I'm ready for you.
Yeah. Here it goes.
Enter visualization request.
Let's try it in the other order.
Circuit code accepted. 6452331 recognized. Beginning message.
Grand experiment of the ancients to use the technology of elemental manipulation to create a completely viable ecological and social microcosm. This microcosm was then to be transported to a distant biosphere, Terra, to supplant its indigenous ecosystem. The need was acknowledged for a central controlling unit capable of compensating for expected anomalies.
Well struck. That looks like a fatal blow.
Yeah, die!
My death will not save you from our wrath.
Are you going to plug me into Link, sir? I hope you know what you're doing.
Yeah, no idea what we're doing. But,
Something is happening, I think. Yes, I'm gaining control. I found my destiny, Mr. Foster.
goes in the middle. Perhaps we didn't even need to know that. The yellow crystal is over on the left side, and the blue one is on the right side. Switch to Annie, have her pull the lever to close the trapdoor, have her push the switch on this side, switch to Zack, have him push the switch on this side. On our way through this wall. Another mini boss. Hi guys, welcome in. Go to yet another development stream in the Secret of Hyperborea, part 6 in this case. Been a relatively busy week. I've spent quite a bit of time on this. Let's hike over to the old cam. See if I can't. See if I can't. Show you a little bit of this. That's about right. Oh, it's a little bit too high. Let's see. I suppose you can see almost all of it now, right? Yeah, that seems about right. So fairly early on this week, I ran into, shortly after the last stream, in fact, I ran into issues with, I ran out of space at our current memory location. We were C64, the C128 memory basically starts the roughly 0, which is here, and there's a bunch of stuff there, the 0 pages there, which is where the fast access variables exist and so on, and then there's a bunch of variables that the software of the machine is using in front of that. And, that goes on for a bit, but here at roughly 1300, this is at memory address hex 1300. This is the start of the basic variables. So if you're using basic on the 128, and the basic variables, they go here, and there's a bit of space free here. Not all of it is free, but there's a bit free. So if you aren't using basic at all, you have a bit of a space free over there. It is roughly until 1C00, which is the start of the basic RAM. That's where the basic code goes in the machine. So you can safely use this space up to the up to this point, which is 1C00. It's 1300. This is 1C00. You can use this space. It's about 900 hex bytes. that you can use over there. Let's see. So 2,300 bytes decimal. We have about 2.3K of RAM sitting here that you can use. Now, for the program to load correctly, what goes into 1C00 needs to be the sys command, which is basically just we're using just a byte array to feed that into the basic RAM. It's done in the main code. Let's just show you here. Easier to show it than it is to explain it, perhaps. So right here in the code segment, which is loaded directly at 1C00, we have a byte array, which is some 12 plus bytes, which is just a line number 0, and then the command sys 7181, which tells it to jump to 1C0D, which is basically right after this command is written. That's where the start of the assembly program is. So when you load the main program on the 128, this will go into the basic RAM. So if you do a list, it will show this command 0sys7181. All that does is tell the 128 to jump to this memory address in decimal, which is happens to be 10CD in hex, and start executing from there. That's basically where this main routine lives. So and we have another issue, which is if we take a look at the memory map of the 128. I'm just going to borrow this the graphic that's on the dev website. The 128. I'm just going to paste it here into the node document that we're looking at the moment. We take a look at this. This is the memory map. And you can see that there's a bit of common RAM here. That's the start of memory. That's the 0 page and the common RAM. And the WIC screen memory is here. Then you have the basic runtime stack and the kernel variables which live in this space. And since we're using the kernel, we can't eat this. Technically, we could overwrite sooner. We could overwrite at 1,000, but that's cutting it close because there are also variables sitting here. Then you have this space that I mentioned before, from 1300 and up to 1C00, which is used for the basic variables, which is technically just free memory. Then you have the basic RAM that I mentioned before. Now you see our dilemma here is that this block from 1C00 and up to 3999 is fine, but then you collide with the basic low RAM. And by default on the 128, when you turn it on off, obviously both the basic low and basic high RAM are actually in place in memory. So there's a precious little actual free RAM space in the addressable address space. So one of the first things that main does now is swap this out, but my problem before I made these changes is that to fit the code, I was obviously loading all of it into 1C00, and once it reached the point where it was filling too much of this memory, which is the low RAM, I could no longer execute the code because the RAM was in the way, so the subroutines were inaccessible. So what I ended up having to do was split the program into 3 separated modules, and we were sort of already doing that in the code itself. So we have the main routine, which is here. That just calls a bunch of subroutines from many of the other modules. Does all sorts of stuff, including calls the init routine, and then it draws the message boxes on screen, and then it goes into the main loop and so on. But the main routine is not actually particularly big. It's just calling a bunch of stuff. Then we have the utility module, which is has a bunch of just common stuff in it. Has some routines like print integer and find center of the string, and a string length subroutine, a multiplication subroutine, a division subroutine, a subroutine to switch the CPU to 2 megahertz and back to 1 megahertz. It has the init routine. Hey there, Gleason, welcome in. Better halfway than no way. Then we have the init routine, which basically sets up the VDC, the various registers on the VDC, and preps the display. And then we have the exit routine, which just tries to restore us back to normalcy as much as possible. And then, of course, we have utility commands like load assets, which loads the sprites and the graphics and the font from the disk into RAM, and some other utilities as well, swap colors, and so on. And this is also where we'll have the routine that figures out where the user is on the map and decides where to draw it. We'll come back to that in a bit, but this is the utility module, and this particular module is now being loaded into this space. So we load the utility module into the free RAM that's available here, the 2,300 bytes that are available here, starting at 1,300. So this is now utils. Then you have this pretty big space here from 1C00 and up to 4,000. Now this is, at this point, we're using this for the main module. So the main module goes here. Yeah, this is more like a function-based programming than it is object-oriented. The object-oriented in an environment like this makes very little sense. I do understand both, and both have their merits, but I think people have gone overboard with the object orientation in some cases. They're using it where it perhaps doesn't directly apply. Now then you have another 4,000 here. It's a very badly drawn line. Do that again. This is obviously not completely to scale, but you get the picture. This is 8,000. It's a very solid 8 that I made here. Very bad 8. This is 8,000. Now, this is graphics. Graphics subroutines, all the routines to write to the screen, they're all here. They're all currently located and sitting in this space, and this is by far the largest part of the program right now. It's something like 8K. So it needs quite a bit of space. The routines to draw the walls and the sides are complicated, and they take up a lot of space. And there are plenty of routines in there to set things up, to draw the window, to plot the text on screen, put the font there. It's by far the biggest part right now. And that now has its dedicated space in memory, and that's basically the routines that had caused the issue of running out of space. And this is 16K of memory. It's enough for quite some time yet. And that we had already done last week. We had already written a routine that uses a space here from 8,000 and really up to C 000. Now this is color should be choose for this. So this place, this is the assets, this is the font, and all the graphical pieces, they go here. We load them from disk and we place them here. Now splitting this up wasn't trivial. First of all, although this looks simple enough to do, it's more complicated than it actually looks. Part of that is, let's see if I can find the switch to the Ubuntu environment, which is here. Find the export addresses script. See if I can't make the font a little bit bigger so you might even be able to read it. That would be nice, right? So what's going on here is that we don't want to link all of the modules together, because if we do so, then every module will have to have all of the other bits linked with it. That would make every module the same size as the complete program, which is completely missing the point of what we're trying to do here. So what we do want, however, is that we want the memory addresses of the routines that we're using to be included in an include file, so we can reference them by their static location in memory. And to do that, we need to be able to create a text file which contains the name of the routine that's being called, as well as the memory address that it's been linked to. That needs to be dynamic, because if we move the code around in the file, it will change. So we can't just hard code it into the file. It needs to be done while we're compiling the code. So this little shell script takes care of much of that. What it does is that it, first of all, it reads the export lines from the assembly files, and I've manually gone through the three files, the graphics, the utils, and the zero page, which is actually linked with every object, but nonetheless, the graphics and the utils are the separated modules. We take all the export lines out of the utils. We remove the load address segment, which is not needed. That's just for the linker, so it knows where to place the module and knows what loading address to put in the header of the file. Then we replace the export with an import, and we make a temporary include file, which just contains all of the routines that are being exported from the graphics routine and all of the utils routines, and puts them into separated include files. Then we compile the code for the first time and make an object file out of it, and then we link it for the first time. And the purpose of this link, which just links all of the modules together, is to create this map. And the map is just a text file. It contains every memory address of every variable and every routine in the program organized into a text file. And we do this once for the utils and another one for the graphics. Then we take, again, all of the exports out, and we place them into a space separated list. That's basically what this command does. It executes this relatively long pipe of various cats and conversions and greps and awk commands, puts them into a space separated list of all of the exports that are in the utils files. Then we go through in a for loop through all of them, and we place the name of the routine with a no line at the start of the line that we put into the include file. And we take the map that we just created. We find the utility subroutines and their addresses. A little bit. You need to be fairly aware of what you're doing when you're doing assembly. You need to know the memory map and so on, and you need to know various bits and pieces of the internals of the machines when you're doing this sort of work. Because this particular map that's done by the linker is actually very useful. We can take the address from here, we take the exports from here, and then I take, basically all of this does is find the actual address of the routine that we already have here and puts it back into the utils files. And it does it for the graphics as well, and you just get a file that I need to shrink this a little bit. You just get a file that looks something like this. Just has the name of the subroutine and the memory address that the linker put into it. So now we can take this particular module and load it into the address space that we already found for it. So we can place the utility module here. We can load it here. And once we've loaded it here, which needs to be done inside the main program, obviously, because the main program needs to load the other modules. So when we start the main program, it needs to load both the utils and the graphics. And once we've done so, we can now access the routines directly from the main routine because we have the fixed memory addresses already in place. And it's the same for the graphics utilities. You can see that it starts at 4000 and you can see the memory address of every of the exported routines here. And figuring out how to do this was a bit of a mess. It took me a while to figure out. Because it relies on two things on this shell script that I created, or three really. On the shell script, on this particular configuration file, which is used by the compiler and the linker. And there I made three separated sections, one for the main module, one for the utility module, one for the graphics module. I specify where they start, how big they are, and then I have separated segments for the code and data, which is for the main module. Data is the variables, code is the code itself, and then for the utils modules I have utils, which is the code, and utils data, which is the variables, and for the graphics routine we have graphics, which is the code, and graphics data, which is the variables. And all of this needs to be in place for this to work properly, because the linker needs to know where it's putting the code, and on top of the files themselves you obviously also have to tell it which segment it belongs to. So at the top of the you have a utils segment. At the top of the utils variables, you have a utils data segment. So that you know, the compiler and the linker knows where to place these. Then in addition to this, we also have a build script, and we already had that, but it's become quite a bit more involved than it was. Because we're also already doing some stuff like finding the correct location of the assembler and the linker and so on, removing old object files. Now it starts by running the export addresses script, which creates all of the includes that we need. And then it rebuilds all of the modules with the assembler again, now using the includes that we already built, which contain the correct names and memory addresses of all of the routines that we need. So here it essentially compiles everything again, and then it links it again, now using just the module itself and the 0 page, which is shared by all of the modules. That's just all of the common variables that are in the lower half of memory, the lowest bit of memory. And then it compiles them into a PRG, and we tell it manually which address to start at. And we repeat this for the graphics and for the utils. And then it goes into the access directory and makes the .dat file. And it copies all of this into the object. And it already places all of this into the object directory. And then it's done. So it doesn't actually take very long. It just builds. And once it's built, we have 3 PRG files now. We have hyperborea.prg, which is the main. It's only 1.5 kilobytes right now. We have utils.prg, which is only 717 bytes at the moment. And then we have graphics.prg, which is 8.5K. So we're not using all of the memory that we've assigned. But we have we have plenty of RAM to build on, so we can keep adding stuff. Now this obviously complicated the main routine as well, because now what the main routine now does is just clears the screen and sets the border and screen closure to black on the WIC2 display, and then it starts loading. It loads the utility routine, loads the utility module, places it in the correct place in memory, and then it jumps to the init routine, which is in the utility module. So this depends on this actually working. It needs to be in the correct place. And then we jump to the init routine. And the first thing the init routine does is put the game is loading point on screen. And, so the screen is black until the utility routine has been loaded. And you get the game is loading bit. Cheers, Lisa, for the raid. And then it, once the utility routine has placed the screen text on, it loads the graphics module, places that in the correct place in memory. And then it starts calling routines from the graphics module, like save the registers and so on, and starts setting up the screen. So it's now a 3-point load. And at the bottom of the init routine is where it calls load assets, which loads the asset game.dat file into memory as well. So this routine effectively loads graphics and the assets, and the main loads the utils. So we've now loading separately 3 different things from the program itself. So the user only loads the main, which is now also just a relatively quick load. We if I reset the emulator here, did I place here it is. I place the PRG in memory. It loads relatively quickly, and all it has is this 7181. Then you run it. It says game is loading, and then it says switch to 80 columns to play the game, and now the game is fully loaded. Game has moved on a bit since we were fiddling with it last, so it now has most of the drawing routines already in place. You can draw. Welcome to your 100% Gleason at your half. You can now draw every type of wall and every type of side in every location. But all of that currently at the moment is being done manually, so you wanted to draw something different, you have to basically compile it in and try it out. And what we're lacking now is our next step, which is figuring out where the user is and drawing the map, which we also now need to place in memory. So that we need to create the map, and that's basically where the other half of the week has gone. After I got the wall drawing up and running, and I was happy with where the sides were and all the walls were aligning correctly and everything was looking okay, then I moved to the next problem, which was how to address the issue of knowing where the user is. If I take you through the concept of what we've done with that. Yeah. This is load assets. Where is this? It's here. How much can we see of this? Might be a good idea to really need the line numbers, do we? It's not particularly useful. Might be interested in cutting that out in favor of seeing slightly more of the screen itself. Better. And I think I need to reduce the size of this text a little bit. So roughly, if we start at the beginning of the thought process here, we have the concept is that every map would be a 16 by 16 map, and there will be no maps that are smaller, no maps that are larger. It's just a one fixed size fits all. It's always a 16 by 16. And the concept that I've come up with is that we'll store it in memory in such a way that the X position of the current user is in the lower nibble of the 8 bytes that we use for the addressing the various segments, and the Y position is in the higher nibble, or the higher 4 bytes. So it's basically an array where you have it's basically an array like this of 8-bit values, where the first value is the Y value and the second value is the X value. So if you need to look up a value for a certain YX combination, you need to address it using the high byte from here and the low byte from here to find the correct value in memory. And this means that we can effectively store this in 256 bytes. And we can fit all of that into a memory location where we only need to change the the low byte that we're accessing, we're not changing the high byte. However, to make things easier, so we can turn the user around, I've decided that I'll use 4 separated arrays, 1 for each direction. So there's a north array, there's a east array, there's a south array, and there's a west array. And the high byte, which is controls the direction. So basically, we're going to have to use 1K of memory for each map. I have an example of this, assuming that X-pos is 8 and the Y positioning is 8 and we're facing north. The array seed is a left shift of 4 on the Y position, and I made up these rules to make finding where we are in the assembly as quick and easy as possible. It's basically arranged in a way that makes it easier to program. And we can find the array seed of the Y positioning by left shifting here to find the high byte. Then we logically OR it with the X position so that we get the lower nibble in. And now we've found exactly where in memory this is. That would be the low byte of what we're going to access. Then we use a couple of different values for the direction, and the values for the direction are set in such a way that it will be easy for us to figure out where the high byte is. If north is F0, then we just shift it once. If it sets the carry, then we're facing north and the high byte is in A0, which means that we'll load the map into A000. That's the north map. That's after the graphic assets, basically. We'll either pad the game data or we'll make a separated map data. I haven't quite decided whether we'll make it 2 files or not. We might. Then we can, if the user is not facing north, then the carry will not be set, and we continue. We shift it again left. If the carry is now set, that means that the value was 40, and we've shifted it twice, so it's now set the carry. So this is basically 128 and 64 that we're talking about here. It's bits 7 and 6 that we're setting. Now if you shift it again and the carry is now set, the user is then facing east and the high byte should be A1. Now if the carry is still not set here, then one of 2 things could be true. Either the 0 flag is not set, which means that the value is 1, because there are 4 potential values here. It can be north is 128, east is 64, south is 1, and west is 0. So if we've shifted it twice, the value is now either 1 or 0. And if the 0 is not set, then it's 1. So then the user is facing south and the high byte is in A2. Now, if the 0 flag is set, then it's obviously is 0, in which case it's now west. And the high byte is A3. We're done. We know exactly where to find the information about this particular segment of the map. For the actual values that are in the matrix, we're using a very similar set because it so happens that there is a command called bit, which is particularly useful for checking bits 7 and 6, and we can use the shifting techniques for the other bits as well. So if bit 7 is set, then it's just a regular wall. If bit 6 is set, there's just a regular door. If bit 1 is set, we draw a wall, but there is actually no wall in place, so you can walk right through the wall. It's a fake wall. And if bit 0 is set, the square is clear. then I've roughly drawn up how we could use this to draw both the sides and the walls. And it's fairly easy due to the way that I've arranged the arrays in memory. If we know the direction we're facing, for example, if we're facing north, and we need to draw the point that is directly to the left of us, because we need to know if there's going to be a side directly next to us, then it's the west wall we're interested in, and we can simply add 3 to the height byte to get to that same wall, and we can then load that value into the accumulator and we'll get the status of that particular piece of the map. Now we can check whether bit 7, 6, 1 or 0 is set here and figure out whether it's a solid or whether it's a door and so on. And the same is true if we're facing east and so on. It's basically the same code, it just changes where the height byte is. And the same is sort of true for the square that's right to us. It's just a different value, because if we're facing north, then it's the east we're now interested in. So we need to add 1 to the height byte and so on. And this should be, if the logic here that I've put into the design document is correct, it should be relatively simple to actually program, because we can just follow basically these steps that I put down, and it should be actually programming it shouldn't be all that difficult. The next step is then, once we've drawn all the sides, there are 4 potential sides that we could be drawing. If we take a quick look at how that looks. Switch back to the OneNote document. I think I have all of them. Yes, I have one that has all of them here, which is good. So these are the sides that you can potentially draw. Each of them are a different color, which sort of makes it easier for us to see. So this would be side 1 left, this one is side 1 right. So this means there's a solid wall on the west of us, this means there's a solid wall on the east of us. If we're assuming we're facing north right now, if we're looking into north, this is west and this is east. Then there's side 2, which is then a square directly in front of us to the west, and directly in front of us to the east. That's in this redder, more bright red color. And there's side 3 left, side 3 right, which is exactly the same, except it's 2 forward on the east and the west. West is this way, east is this way. And then it's the final one that we draw. We never draw more than we draw more than 4 different sides and 4 different walls. That's how long we'll reach for the drawings. Then we again have the east and the west. Side 4 left, side 4 right. So the code that I described before would draw all of the sides that it needs to draw first, and then it will draw the walls after it's drawn the side drawing. At least that's the plan. We'll have to see how badly it flickers. Now, to figure out the walls, we need to see the square that's in front of us. We're obviously standing at the current square, so we're not going to be doing anything about that. We'll see the sides on the east and west side to us if they're there, but what we're drawing next is what is in front of us. So we can simply add 10 hex to the current position to get the square directly in front, because the same x value but a y value higher is going to be the one that's directly in front of us, right? In the same array. Because there is a separated array for north, east, south, and west. So in whichever way we're currently facing, and assuming we're using the same height byte, whatever is directly in front of us will always be 10 away. This is why I decided to use 4 separated arrays, even if it takes more memory. It saves a lot of all sorts of wondering of which direction we're facing, and all sorts of endless issues with checking where we are and which direction we're facing and so on in the code itself. This makes that relatively easy at the expense of wasting perhaps slightly more RAM. Now, we have the rules here for figuring out what wall to draw. We're basically using the same thing here. So the same is true here, that the 128 means there's a solid wall, 64 means there's a door, 1 means there's a hidden wall, and 0 means that it's empty. So we're using the bit to check the value here. And we sort of saw how that was done previously, how we could easily do that. We can use the bit directly with this value and check bit 7, check bit 6, which uses separated flags and then the 0 flag. We can do all of this with just this single bit command. We'll basically set up to it will set up to 3 separated things for us, so we can fairly easily do this. Now, to get to the square in front but 1 left, we simply need to add 15 to the current seed that we have, and we'll find a new seed for the location that's in front of us but 1 to the left. So you can see that this should be relatively easy to do, at least in theory. It should be relatively easy to do. The same is true for finding the right one. That's I think 11. And we repeat this for the first set of walls, the second set of walls, and the third set of walls. And if we've printed any of the walls, we obviously stop. If there's a solid wall right in front of us, there's no point of drawing anything after it. So I've forgotten exactly how much effort I put into this, but roughly if we've drawn a solid, we won't look at the solid behind it, and so on. And I should make it relatively quick to draw something that is that just has a solid wall in front of it, and slightly slower if we need to draw the furthest wall away, which is basically what I showed at the start. So what we have right here is just a solid block of the furthest away wall. So these are 5 different segments of wall. This is as far as we possibly go. The only case where we draw 5 bits of the wall. This is if you can see the mouse on the screen, I might be able to show this to you. This here is the furthest left segment. It's just this 1 row of bricks. If we draw it anyway, then there's another segment that is roughly this big, which is the a second set, and there's a set that's in the middle. There's a set that's to the right, and the furthest right is then here. So if we're standing furthest away, you can see the furthest away, which makes sense. I think I've taken a screenshot. All of these. I could just show them to you. They're all in the Discord. I've done a lot of documenting in the Discord as well. So this would be the third wall, the one that's second furthest away. You can draw up to 3 pieces of that. And there is the second wall, which is the second closest to us. That's this. And then, of course, if the wall is just right next to us, I think I have a screenshot of that somewhere as well. I might not actually. You'll just have to take my word for it that there is one. And you can sort of see how it looks with the sides drawn in as well. This is what it looks like when you have a solid wall to the east and west. Then you have one empty space, and then you have a solid wall. You can see how it sort of wraps around, which I think adds a lot to the... Yeah, good night, Gleeser. Thanks for the well wishes for the stream. Hey, Ava, welcome in. Thanks for shouting Gleeser out. Well, this is basically what it would look like if we had a solid wall on the west and east side, and then you have the empty space here in front, and then you had a solid wall here that would basically look like this. You can see that it's sort of starting to take shape, and you can see here that we have the same situation, except see, this would be the same, except we've wall is one closer to us. You can see that the how this illusion works. Oh, it's there are 2 empty spaces here. There's only 1 empty space here, and if we were to move one closer, we would be standing pretty much in front of the wall. It is, but all we're doing right now is color or wrapping this, and it's particularly a pain in the ass with the it's one of the limitations, and one of the many limitations that I had to overcome. It's the weird issue with the color clashing on the chip, because you can draw anything you like, but the color is only defined in 8x8 blocks. And you can be a lot more accurate with the pixels that you're putting down, but the colors are still defined in an 8x8 block. So if you want to have the sky blue and you want to have this block which extends into the top row, then it will collide unless you make it so that the foreground color of the wall block, of the side block, is the same as the background color of the sky. So the cheat I'm using here is that for every these pixels on the side, these are all defined just as zeros, so it's just using the background color. But for the bit that's I don't know if you can actually see the mouse here. Can now. This bit, which doesn't actually have a background, you need to set this to all ones. So it uses the foreground color, and you need to set the foreground color at least for the pieces that are basically this size here. This rectangle here at the top that reaches onto the top. And the same for the bottom here. For the pieces that basically make up this, you have to set the foreground color to be the same as the sky color on this side and the ground color on this side. That's the only way to get it to not clash, which means that you can't really style this section of the wall or this section of the sky. You've basically used the colors that you have to make it not clash. If you want to style it using different colors, you can do so, but in an 8x8 grid that needs to be outside of the area that we're already using here. And this is basically the biggest problem with this is with the side pieces, because they're obviously not, even if they're multiples of 8 in terms of width, which is very helpful and is actually needed. And I spent a lot of time trying to make them line up perfectly while being all in multiples of 8. It's not 100% perfect. You can see this tiny misalignment here at the bottom. That will just have to do. Maybe we could pat it a little bit here at the bottom to make it look better, but it's roughly in a straight line, and it's a limitation that it gets very ugly if, for example, it's on a half boundary here, because then you have an issue with the colors colliding between the pieces of the wall, which is not good. So this is this is more easily solved than having it clash all the way up here. It's easier to cheat your way around this than it would be to cheat your way around this, or unless you're just stuck with largely having them all the same color, which is not nice either. Not what I've actually done, because the side pieces are different colors as well, as you saw here, for example. They're not the same color and they still don't clash, and that's because they're exactly 8 in multiples of 8 in terms of width. And here I've solved the issue by using this foreground trick that I used to make it sure that the lines perfectly here, and it was quite a bit of work to sort of make this look not terrible on screen. We can still style this, but there are obviously limitations as to how much we can do so, and I'm no artist, but if any of you want to take a crack at trying to make this look better, that's fine by me. Just considering the limitations that we have, is that you can, every 8x8 block can have different foreground and background color. So that's your options, and you have a fixed palette which you can use, and you can only basically apply the styling in this sort of box-like figure here that doesn't collide with the sides. It's easier, far easier, with the bricks themselves that make up the wall. This you could style. All of it. It's all on an 8x8 boundary. And you can style it like you want. It's just the sides that are located back and forth. We're not padding these in any way. So these are just solid blocks of color. And you can do whatever you want style-wise with all of these. And they're also easier to draw because they're all very easy to copy. You can, in the code that makes up the wall, what it basically does, it draws a single brick, and it copies it 3 times to make a full row, and then it copies the entire row 3 times to make all of the wall. So that's relatively quick, while drawing the sides basically requires you to manually copy every single byte into memory. So that's quite a bit slower. So drawing the sides takes many times more time in terms of wasted cycles than actually drawing the wall. So you can draw multiple walls in the same time it takes to draw one side. Because the graphics chip can do most of the work of drawing the wall itself, while you need to just manually draw each and every pixel with the sides. So that's a drawback, but it might end up looking okay. I actually think this looks okay. It's definitely good enough to test out the engine and figure out how to draw the user in space and so on. It's perhaps not enough for a finished game, but it's certainly better than I actually expected when I started working on this code. I'm reasonably happy with it, at least. So switching back to the code, Now, one of the jobs that we have is to draw this routine, and obviously I've made up all of these arbitrary rules about how these arrays look and what values are in them and how to turn around and how they're split into the separated arrays and so on. We're gonna need to have some way of creating this, and that's where our good friend the map maker comes in. That's what I've basically been working on for the last 2 days or so while I have time away. I spent maybe an hour and a half, 2 hours every day working on this project, and I use the time that I would usually be using to watch Twitch or whatever, the time that I spent down here in the dungeon. I use that time to program. Sometimes I'm also listening to someone streaming or something while I'm doing it, but I'm maybe not very actively engaged because I find this project fascinating. It's taking up a lot of my time, and even if I'm only spending like an hour and a half, maybe 2 hours a day on this, I still get quite a lot done because often my brain has been thinking about how to solve something for most of the day, so when I actually sit down I can basically just start processing whatever I've been thinking about during the day. Now, where is the map maker? It's here. See if I can show it to you. Can't see the top. Sort of a problem. Why is it that you can't see the top? It's not being cropped. Why can't you see the top? Perhaps because it's not capturing it correctly. You'll just have to trust me. There is a menu at the top. You'll have to trust me. There's a menu at the top that you can't see on screen right now. So what the editor does is that it just tells you which color is what, and just prints out this little 16 by 16 grid. So you can, and then you can go and click on any part of the map. You can see the part that you've clicked on becomes highlighted. So you can see what you've selected. Then you go down here and it tells you exactly where it is that you've placed it. It's X7, Y4, and the direction is north. And you can pick whether it's an empty or a solid or a door or a fake wall. And if you click here, change it to solid, it will change it into a green pixel to indicate that it's a solid. And you can basically do this like this and so on. Just draw the map, and then you can either save the map using the menu. There's a save and a save as, and there's also a load. I'm going to use the load now. We can basically just load in a map, and this is a way to create the map, and the map is basically the arrays that are discussed in the game. It creates a save file which creates those 4 separated arrays, one for each direction, using the same values that have been discussed before. So it's basically making up exactly what it is that the game wants to load. And having something that allows you to draw this in some easy way and then create whatever it is that the game actually needs to load is pretty much invaluable, and we're going to have to create more tools like this because they save a ton of time. I were to try to code this directly into the arrays themselves, that's a massive pain in the ass. It would take forever to do. And this makes it much easier to make up different maps. And since this is just a Python program, it runs on Windows and Linux and Mac. All it needs is this GUI0 Python module, which is has an installer for Windows and is easily available both on Mac and Linux. I could port this around, and you could just get a chance to play with this yourself and even create your own maps. It makes it fairly easy. You can just send me the map file and I can import it into the game. And we need a way of loading the maps in and out of memory. And we need to add a lot more, because this is basically just in terms of the map, this is just what bits are solid and whether there's a door and so on. But obviously there's also going to have to be some sort of action. So I've intentionally, there are obviously 8 bits that are available in the each byte of the array, and I'm using 4 of them. One to signify that there's a solid, one to signify there's a door, one to signify that there's a fake door, and then I'm using the 0, all 0 to signify that we're actually there's nothing there. That leaves bit 2, 3, 4, and 5 that we can then use to represent something else that's supposed to happen, because we need some way of creating a trigger. And I'm thinking that one thing we could potentially do is just use the bits that are free as a number to indicate that some sort of number in a lookup table to indicate what action is actually there. That's one way. So if we were to if I move back to the node cam, we're already using, if we take a look at the different bits that we have. So we need to think about how we maximize the little memory that we have. We're already wasting quite a bit of it. We're already using this. This is solid. Already using this. This is door. We're using this. It's this is either, if it's 0, then it's empty. And if it's 1, it's hidden wall. That leaves the rest of them. This is green. This is red. This is either blue or empty. So we have a few bits that we aren't using. We have this bit. This is a 5, 4, 3, 2, 1. I have these bits that we can use. This can be a 5-bit value, which perhaps isn't enough, but to trigger some sort of action, but might be enough to mean that we could use these bits to signify that there's something else happening on screen, or there's something else that's supposed to be happening. So for an example, we could use bit 5 for an encounter. For example, bit 5 is set, and whenever you hit this particular square, there's an encounter that takes place. We could do that. We could use bit 1 to represent some sort of special square, something that happens. Like you enter a store, or you enter a tavern or an inn, and so on. It's not an encounter, but there is something special that happens. And we could use the different bits for different things. We just haven't decided what we could do with them, but there are at least enough bits. We could easily find them. And for the various actions, we don't need 4 arrays to describe those. So let's say that bit 5 is set for every encounter. We could have a single 16 by 16 or 256 byte array that would describe what would happen in a certain location on the map in terms of an encounter. So it could be relatively easy for us to fit that in memory. We don't need as much memory for it, but potentially we would need to have a few of these arrays, one for the encounters, one for the specials, and so on. We'll probably need at least another K of RAM to represent this, and probably more than that. It's probably going to need to be something like 4 kilobytes in total that we use for this, but that's still manageable. We still have a bit of space, and I've left the bits here free so we can roam around and do this. That should be once we get to that point. The plan is then to add that to the map maker, so you can use the map maker to set up what exactly happens and what exactly are the consequences and so on, using this program, and then save it to make the map that. And once that's in place, you can then place it into the game using the routine. That's one thing that needs to be done. And the next step is just to try to get the map loaded into the game and try to figure out this routine to actually draw the walls and so on. That's step 2. And then we need to start working on code to move us around and get us working within the boundaries of the map that we've already drawn. That would be very nice. And once we're able to do that, even if we have no encounters or nothing, then we can start thinking about how to add the actions. And pretty similarly in time, then I need to make another helper program which needs to take in a graphic file and convert it into an image file that can be needs to be a fixed resolution, and it needs to have the colors in 8x8 blocks. So what I need is I need to be able to import a bitmap file containing some piece of graphic, and I need to be able to convert it so that I only pick 2 colors, one for the foreground, one for the background, and it's all in an 8x8 cell. So that's the format that we would need for the graphics to be able to plot them onto the BTC screen. Because we're gonna need to have some graphics at least for the taverns, the inns, the blacksmith, start of the game. Going to have some images which we can actually draw on screen. So we need something to I could find some assets for most of that stuff, but I need something that can take the asset and make a valid file that I could just plot to the screen using that. And there's a bit involved in it because there's obviously the bitmap itself, which is just a pixelized byte that describes which pixels are on and which are off. The off pixels get the background color, the on ones get the foreground color. And then I need another color map which tells me which background and foreground color to apply to each 8x8 square. It's basically two separated things that I need. One goes into the attribute memory, that's the color memory. The other goes into the pixel memory. So somewhere along the road, that's next. But I have a feeling most of next week will deal with actually putting us into the map and making us able to move around, and then we'll sort of get a feeling of how slow it is. I have a rough idea right now how slowly it draws, because the game is set in such a way that every time I press one of the buttons it does redraw. And for a while I had some glitches on screen because it was drawing over some stuff. It's not, the good news is that at least now it's not unbearably slow. So I have a feeling it's going to be okay. At least I hope it is, and if it isn't, then if it's too slow, we have some ways of trying to speed it up a little bit. So we'll cross that bridge when we get there. For now, we need a new routine. Or we need to add to the load assets routine. Something that deals with loading in the map data. And we need to write some sort of C program that puts it into the file. Or we could just take the file directly, the map file directly. Maybe we would just do that, we'll see. There'll probably need to be multiple maps. Think of how we could place them, whether we can seek into the file or whether we need to have it all in multiple files. I'm not sure, we're just using the kernel routines to do this. Right now I've only been able to see them load entire files, so we might need to split it into multiple files, but we could also just, I sort of need to know how much RAM we'll eventually need for all of this to see whether we have the space to load maybe multiple things into memory at the same time. The last bit of the memory, the one that has the assets in it, is you can bank it, because the C128 obviously has twice the RAM as it has addressing space, and then it has RAM for a third bank really. So we have 16K of free memory on the upper half of memory we could use. Potentially we could have more of the map loaded and just switch between the banks when the user is exiting one map and going into the other one and so on. Well, that's one way we could potentially handle that. We'll think about it, how best to approach this when we get there. But for now, we need to go into the to edit the variables here. Make a new one. Just for now, we'll call this map.dat. And what we'll do here is need to know the file name length. We need to know that into the accumulator. Map.dat would be 7. And then we need to tell it to make a file name pointer to the string. Then we call a kernel routine called setNam, which sets the file name to be loaded. And we set some basic things, which memory bank is being used for loading, which memory bank is being used for the function bank. And then we call the kernel set bank routine, which just puts these values into the correct location in memory. Then we set the file. This is meant if you have open files that you're actively working with and saving to and so on. We just use 0. And we set the device manually here. You could, in theory, at some point allow the user to select the drive that they're actually using. So we could, right now it's hard-coded to use drive number 8. Now we set the secondary address for the SA to FF, which means that it will use whatever is in the header of the file to place the file in the correct location. Make that have to take the map file and put the correct header address in it, because it needs to put the A00 header address in the file at the front of the file before it starts writing the file. So we're gonna have to pipe it through something that sets this. And then we call the set LFS routine, which sets the logical file number and the device number, which reminds me, I should probably put some background music on, right? Forgot about that. It's eerily quiet. That's better, right? I'll set the logical file number and device number. And there are a couple of other parameters that we need to set. We need to set whether we want to load or verify. 0 means load. Anything else means verify. And we have to set these to low and high memory address. You only really need these if you want to manually set them here, but since we're setting them from the file, we could also potentially try to do it this way. Maybe this would just work to load it directly, then we don't need to pass it through something else to load it. Might try it. Quickly see if it works or not. And then we'll jump into the kernel load routine. And we have an error segment. If the kernel load routine has an error, it will set the carry and we can branch to the error routine. doesn't actually do anything currently with the error, but it does read it to get the IO status, but it doesn't actually do anything. It just returns again. So if it doesn't work, it will just not work. That should be enough to load it. Then, in theory, we should just be able to copy one of the maps. Just copy the map that we had in the map maker before. Into map.dat. I'll just do that right now using the command line. It's now in the object directory. So if we reset our good friend Mr. Wise. It's funny how almost none of the shortcut routines in Wise actually work on my system. All of the shortcuts that they're actually using are being used by something else. Map.dat is there at least. See what it does. And it loaded at least. There's no red blinking light on the disk either. See if I can. I need a way to show you the monitor now. Just delete this bit. I have so many overlays that I'm using for this. Keep adding more. So many things that we need to switch between. That's roughly it. There we go. That's the monitor. Now we're interested in the RAM, and particularly we're interested in something that's stored here. It actually looks good. That looks pretty good. This at least is the door value. Not sure why there are so many F's here. take a quick gander at how the actual map file looks in hex. No, it's not the same. Maybe the 40 there is just a random. See, to exit the monitor, be able to build the code. I made a single change here to the code and recompile. Let's see if that fixes the issue. Might. Time. Roughly the same. Curious if it's being loaded somewhere else or where it placed the file. I have a feeling it placed it absolutely nowhere. Okay, let's go back to the code. Now that it's calling this routine, it's obviously still loading the prefix. This is correct, and we also verified that the file is there. Setting it to 0, which as I remember, is correct. We might have accidentally swapped this. This might be the other way around. The high might be first. Or it might be this one. That could be the issue. Let's rebuild. Still not there. Obviously not here either. If it had loaded it to the exact opposite location, I probably would have crashed. That address is definitely being used for something else. parameters for this routine. Starting with set LFS. It's the lower byte. It is the lower byte that it's supposed to be in the X register. This was correct the way it was. It's supposed to be like this. I wonder if it's actually branching here. Could explain why it's not returning. You can easily figure that out. I'll just put, that's why I left the print integer routine in. It really serves little point at the present time, but I use it to figure out whether code is reaching a certain place. It's a quick and dirty way to figure that out. Rebuild it. And I'll put it in again. And what's the 40 column display? It's not reaching the code, it's not printing anything on the display, so it's branching after the first call to game dot. Not sure why it does that, because there's no error. Obviously loading the game dot file. But it's the branching code to the error that is causing the issue. I'll remove it temporarily, and I'll rename the files and figure that out later, whether it's simply not true that it sets the carry on an error. Maybe it sets the carry when there isn't an error. It's reversed. Maybe I'm misunderstanding what the error means as well. That's entirely possible. Let's see, it's actually... Still not loading. Why not? You could see the two that plopped up there. Does it pop up here as well? Yes, it does. It's definitely being called. But it is moving down here in the code. Now I'm curious. It should be returning the addresses it's actually putting the file in. I'm going to temporarily stop printing the switching text. So it doesn't overwrite what we're trying to do with the debug. See both of the twos right now. Want to see what's being returned there. It's turning something else at least. obviously it's not. It's not doing this the way I would think it was. Might be working better now. See what the monitor says. No. Maybe there isn't an easy way to do this. I might as well just spend the time putting it into putting the header into the actual file. Time might be better spent that way. Shouldn't be a major hassle to change game data to do that for us. Where are we currently? 8A60. Okay, map.dot. Call that map. Now, this is what we're doing with the asset file. I'm gonna have to do something very similar for the map file. You're up to something. Just reuse this bit of code here. Change this. For now, we'll just statically define the map file. Where was it again? Relative. Map maker maps. And Andrea.map. It's the incoming map file. We'll put that into map in. Close both of these files. Because I have to read from them as well. We have a buffer called buff here. We'll use that. We'll feed from into the buffer. Use size unsigned car. It's just a single byte. The count is 2024, and the input file is mappin. Read this into buff, and we should be able to do something very similar with fright. We'll do fright to should be the same buffer. Right. I should copy the file in and out. Two food arguments. Compiled. Did it generate map dot? It did. It's 1026 bytes, which is also roughly true. Just open it up. See what's actually in it. Yeah, it's the same except the header at the start is different. So that worked just out of the box, which is nice. So now we need to change the build script slightly because we needed to do this instead. Okay, now we rebuild this thing. Back to the load asset code. Now we use this and we set these to 0 to indicate that we want to use whatever value is in the file instead of routing it to a fixed location. And we save. And we rebuild. Run this code. See what happens. Guess we should check the monitor. Basically our only way of seeing what's going on. Still not doing what I wanted to do. Still roughly doing exactly the same thing. It's not putting it somewhere else either. Okay, I want to try one thing here. I'll close this. Now that we have the address in the file itself, we can also do something else which we couldn't do before. We can just load it directly. Instead of loaded now, it should be in the correct spot. It is in fact not. That is interesting. Why is that? The file itself looks fine. Just going to verify. This worked correctly? It does. Let's do a hard reset. Activate the monitor again. There's nothing in 8000. There's nothing in A0. That makes sense. Let's load game.dat. There's something in 8000 now. Makes sense as well. I'd expect the same to be true for this as well. It is. Okay. There's something there now. Let's load the program back in. Have it load everything. And go to the monitor again. This is fine. This is not okay. I load the file manually. I load the file manually. It seems to go into the monitor. This is correct. You can even see the maze here. Tick, 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 tick. You can sort of see the imprint of the maze in memory. Sort of follow it around, so you can see that it's obviously the maze that's being loaded, so it works if you load it manually, but if you have the game loaded, it doesn't work. Well, there's still something fishy with this code. Wonder what that is. It's basically just a copy-paste from the previous code. Certainly not very complicated. We might clear the carry here. The carry is set after the kernel load. That might possibly be the issue. Fairly sure this is all correct. It's almost impossible to typo in this. Build it again. Loaded now. It was the carry that was set. I was disturbing it, so I'm not sure why it's actually setting the carry, because it does load the file. Hey there, Caesar, welcome in. Thanks for the follow. Okay, so it is loading now. I need to look into why the kernel is returning with the carry set. It really should not, because there's no error. It obviously loads the file. Then it loads the map file now as well. Sort of strange. never mind. Never mind, at least it's loading now. So big peek into the monitor, and it's obviously in memory now. You can see the imprint of the map here. That's in accordance with the map maker. Let me just quickly fire that up again. There's the maker again. We open the file in the map maker. That's roughly what it looks like in the map maker. That's roughly what it looks like on the monitor. The 40 is the door, so you can see there's a door here, there's a solid wall here, there's a door here, and obviously there was this value 01 that's over here. That's the hidden wall. Obviously we're just viewing the north side of the map. Multiple arrays, obviously. This would be the east side of the same map. This is the south side, and this would be the west side. All just depends on which viewpoint you're viewing it from. Obviously, it's all very similar. And what the maker does is that one thing that I didn't explain about the map maker before, and we should probably talk about that as well, is that obviously if you click this square in what is essentially x5, y7 facing west, and this is obviously the same wall as this wall, which is x4, y7 facing east. So what the maker does, it writes obviously to both of these values when it's writing it out. So you put the door here, it writes it to 5-7 facing west, and it also writes it to 4-7 facing east, because the same wall applies, the same door applies. I meant to say, obviously if you're facing it from the east, you have a door. If you're facing it from the west, you also have a door. It's the same door, just from different sides. So in theory, at least in my primitive brain, it works perfectly fine this way. Now let's see whether we can actually use what we wrote down to get moving on placing ourselves in the correct position. Now, these directions are all fine and dandy. The question is, do they actually work? I'm going to cheat a little bit here to start with. What I'm going to do here is put us in a fixed position on the map. To start with, what should I call this again? I'd given it some thought at least. Maybe I hadn't actually put it into the 0-page file. the direction here, obviously. The wall type, it's already here. It's fairly sure. I think we should call this user direction, user expos, user ypos. I think that those are the good names. We need a way to store what the x and y pos of the actual user is and in which direction he's facing. So what I'm going to do here is just going to place us somewhere. We'll be in seven, 8, facing north. Means we're here in this square. 7, 9 it is actually. Right. Yeah. 7, 9 facing north. That should place us right there. I'll just put this before we call the forever loop. And we'll go into draw game. Draw game has roughly been just a sketchboard while I've been working on the various different pieces of the actual drawing code. So I'm using this direction variable for something else. I better take a look at that. I'll call this user action. It makes more sense that way, because that's a totally different thing. User action, because what we're storing here is what the user actually wants to do. I'll totally ignore that for now, because when we enter into this routine, what's in the accumulator is the actual key code that the user pressed, and obviously you're supposed to use 8 to move forward and 2 to move backwards, 4 to turn left and 6 to turn right. So these are just the key code values for these, and we'll come back to this. Right now we'll just ignore those. I'll also just not draw any of this stuff. I'll comment all of this code out. They can stay in here just as a reminder of what I was doing. For now, the remnants of lots of testing and debugging here, of which there's been quite a bit. Figure out what to draw. There are more things that need to be set here. User dir is the direction the user is facing. User expos is the exposition of the party. Party is perhaps a better name as well. party X pause, party Y pause, party direction. Probably an even better description. Party X pause. Party Y pause is the Y position of the party. Somewhere in the init code for the game, you need to place the user in a map. Of course, if you load the game, the position should have been saved with the game, but at the start of the game, you need to place him in some sort of map, in some sort of position. That's what the init routine should be able to do for us before we get here. So these all have to be set before we make it in here. And now we should call... What did we call this routine again? It's called... What is it called? It's not called anything at the moment. Maybe it even doesn't belong here. Perhaps this code should be in the graphic subroutines, but there is a bit of figuring out to do. Sort of reluctant to put it into the graphics routines because I just call the routines from the graphics routines. Just wondering what to call this routine. So this routine is already called draw game. I'd call it view. The problem with that is that draw game is a pretty good description of what it does. The question is then just what we call this one. Maybe it should just be the same routine. Maybe it doesn't make any sense to put this in another routine. Just copy all of this blurb here. And we don't really have to jump anywhere. Put the blurb above this. Now to follow my own instructions. Which is sometimes a good idea. Let's go to that part. I don't have enough resolution while I'm actually working with OBS running to have the split screen view that I usually have in this file. I'll just open the file in another window. You won't be able to see the comments. Pretty fine. The first thing we need to do is figure out which of the sides we need to draw. What we need to do is we need to figure out the low and high byte of the value in memory that we're interested in. And for the sides, the first side we're interested in is the side that's directly to the west of us. So that's the way the routines are ordered. Let's quickly recap this again, because I can spend all day talking about something and you might not understand it anyway. So just very quickly, the sides that we're going to be drawing, so we're on the same page of what is a side and is it a side. These are the sides, and the crimson blocks that are closest to the user that I'm currently drawing these blobs on. This is the left side 1. This is right side 1. Left side 2, right side 2, left side 3, right side 3, left side 4, and right side 4. So these are the sides that we want to print. And we'll print a side if the squares west and east to us are solid walls, or otherwise not. And we'll print something else. Obviously, at some point we'll need to print a different side if there's an actual door. We'll need to figure out a way to somehow map that to the side. We need a way to represent a door on the side, so we'll need a different graphic for the side that has the door, but other than that, for our intents and purposes right now, it's not important. We'll just draw a solid for a hidden wall, for a door, and for a solid wall, and if it's empty, we'll draw nothing. That's we eat the elephant one piece at a time here. Putting the code in for the wall is not a terrible additional complication. It's just I need to add the drawing code to the side drawing, and I will have to pick a different asset from memory when it's loading, but the drawing is still the same. It's just you have to point it to another memory address to draw the actual side. But otherwise, the code for the drawing is the same. It's not a big deal. It's just a single conditional to add. Now, we need to take the Y position and shift it. So let's load the Y position into the accumulator. Shift it left 4 times. Put it into the higher nibble, and then we'll or the value that we have. Or it with the X position. What theoretically happens now that let's assume that Y position is when we go in here is well, we know where it is when we set it to something. Where is it again? The Y position is 9. That's represented in memory is in binary is as 0 0 0 0 1 0 0 1. So byte for the 8 is set and byte for the 1 is set and 8 plus 1 equals 9. So we shift it 4 times, after which it will be 9 0 hexadecimal 1 0, or it will be like this. So effectively decimal be 144, because this is 128 and this is 16. 128 plus 16 is 144. That's the higher nibble, and then what we do with the X position, which you already know what it is as well, it's 7. And we OR that. Just place it at the bottom here. It's 7, so it will be 0 1 1 1. So now it's 144 plus 7. Just 151. That's the array sheet that we're actually referencing for 97. If we imagine the array looking like this, and this being y and this being x, then it should be 9 times 16 plus 7. That should gain us access to this. That's also 151, so this calculation is perfectly correct. So my thinking was straight when I did this. And, the cumulator should now be 151 after we've done this. We should have the correct position in memory. The aura should take whatever is in the expos, whichever bits are set there, and OR them with whichever bits are set after the shift, so it should effectively do exactly what we want here. So now we have the low byte of the array. There are 4 arrays, 1 for each direction. Now we need the high byte, and the high byte is tied to the direction. That we can do statically. So now we load the party direction to the accumulator. Party dir. We compare it with we bit it really. That's what we want to do. Bit it with 11000001. We're interested in first 2 bits, and we're also interested in the last bit for the direction. Because for the direction, F0 is north, 40 is east, 1 is south, and 0 is west, and the way this works is that F0 is binary like this, 1 0 0 0 0 0 0 0. This is north. This, however, is 0 1 0 0 0 0 0 0. This is 0 0 1, and this is obviously all zeros. What a bit command does, which makes it particularly nice for this purpose, is that it does a comparison of multiple bits, and it sets multiple flags at the same time. It's very efficient in terms of not having to do this multiple times and saving on CPU space. And it will set 3 different flags. So once we've done this, it should have, if bit 7 is set, it will have set the N flag. To temporarily store this in memory to use bit. Doesn't seem like it works in immediate mode. If that's the case, then we can save some cycles by putting the comparison and into the 0 page as well. Just call it map comp. Not sure what to call it. We'll load it here. The accumulator with this value 1100.0001, store it into map comp, and we'll bit it here with map comp. What that effectively does is it ANDs whatever value is in partitir with this binary that's already in map comp, and it sets all of the different flags, and bit 7 was set and the negative flag is set. Bit 6 was set and the the overflow flag, sets the overflow flag with bit 6. And it sets the 0 flag with 0. And obviously, since we only have Because if you only have these particular values, then it's fine, because if it's not 0, then it's 1. If the negative flag is not set and the overflow flag is not set and the 0 flag is not set, then it's 1. So we don't need a separate bit to test for that, so we can just branch on different results here. First one is BMI. Branch on negative. Branch on result minus, as it's actually called. And we have BVS. Branch on overflow set. Which, then we have B&E. And then of course we don't need to branch anymore. On bit 7, user is facing north. Facing east. User is facing south. User is facing west. Branch to north, east, and south. And if we end up here, the user is facing west. To save this in. This map. It's 2 bytes, a high and a low. I seem to remember put a macro file for a little bit here. Refresh my memory. High byte is the +1. Map array. What we want to do is we want to store this into map array. This is the low byte. In this case, it's I refresh my memory of the memory location for the different directional arrays. The user is facing west. The west map is in A3. So we'll load A3 into the accumulator and we'll store that in map array +1 high byte. We'll jump to something we'll call array is set. I'll make a little point here. Then we'll have to create something called north, and that will load north is a0. Store that in map array 1, and then jump to array is set. East is a1. Store that in map array +1. Jump into array is set. And south, load a2. Store that into map array +1. Jump into array is set. I like to over comment this code. Helps me when I come back to it. Tends to be over commented quite a bit. All of them end up here, so this is where we continue. Now we know how to access it. Now we need to load it into the accumulator. We need to do that using an offset. Do here is we use indirect load x with 0 here. Just start by accessing the map array directly. This will take both of the bytes, apply them together, and load whatever is in this particular memory address with this offset, which is currently set to 0, into the accumulator. The value of A now should be, since we already know we're facing north, it should be A0. Whatever this was 151, right? A097. So the accumulator at this stage should be A097. Well, the value of A097 should be into the accumulator exactly at this point. That exactly that I placed us here. So there should be a wall on both sides. We won't get much further tonight, but let's see if this theoretical code at least works. To make at least one attempt at this. side one left. If my calculations are right, then all we really need to do is change the high byte, because if there's a solid wall to our west, then if we load the exact same position facing west, then there should be a solid there. At least that's the theory. Let's see if that's actually true. We'll load the high byte in here, increment it 3 times. Now it's cheaper to we have a fixed number. It's cheaper to load it into the accumulator. Just ADC it. We just need to make sure that we clear the carry here. Just add 3 to it, store it again. And we'll just access it like this. Now we'll compare it with should really bit it with map comp. Compare array value to left, find the piece west of us. Load volume into accumulator. Compare it to the map comp. Now we have a similar situation. This is a solid wall. This is a door. This is a fake wall. The only case we're not interested in here at this current point in time is if it's X0. So right now it's just back to no left side 1. So put here. So if it's 0, it will jump. Not print any side. If it's anything other than 0, we'll just continue with the code. So at the moment we're doing exactly the same thing for all of them. And continuing with the code in this case is to just draw the left side. Draw left side 1. There's no left side 1. Let's see if the code even compiles now. We've made a bit of a change. is it complaining about this? Yeah, that's because it needs to be the Y. It can only be the Y register if we want to do this. Really, for all intents and purposes, this is sufficient right now. Doesn't even need to be. We're not actually using an offset at this current point in time. We'll use that later. It's not supported to do it without it. We have to do it like this. So VDC draw side 1 left. We need to export all of the zero-page variables that we've added here. Party dir is undefined. Party direction. Do we have some more as well? This was supposed to be party ypos, party expos. I was wondering why that didn't error. That's why. Map comp and map array. Should be map comp, right? Should be party dir, party expos, party ypos. Easier to read like this. Fix it in the code. Party dir, map comp. It. Getting close. It's almost building now. Still an error. Yeah. It's also the user action. Previously exported here. We need to fix this. So Xbox user ypos user direction. That's right, we named it party expos, party ypos, party direction. It's not the user, it's the party. It's an error in the zero-page file. And it's missing a colon here. Places. Now it built. Close the monitor of this doesn't work out of the box, we're just leaving it here. Plenty to do still, as per usual. Some progress though. Nope, doesn't work out of the box. Doesn't draw anything, but it is doing something, which is nice. This will need debugging, and I'll continue just rambling on with this code and completing this. That's mostly just manual labor, and we'll see if I've made decently good progress this Friday. I might do another stream where we'll look into moving around in the 3D space if we're at that point. I'm able to move around in the 3D space on Friday. I might do another stream then. We can figure out some things and maybe draw a bit of a map and see how things work, and you can sort of see the game semi in action, and then we can start working on other things. And, I think this is a good place to stop at this point. It's already 1 AM over here. See if there's anyone on we might be interested in reading. At this point in time. I'm wondering if there's someone actually doing any development. pixel art game. Let's just go random. So I don't know who this is. It's just a random person. Maybe it's better left undone. Yeah, perhaps it's better left undone. Just skip the raid for now. I'll head to bed and perhaps do another one of these on Friday. Thanks for coming in, guys. Thanks for staying here. It's more fun with people here. Thanks for every interaction in chat. Thanks for the raid again, Gleezer. I'll see you guys here. Definitely Saturday for Might and Magic 6, but if not, possibly Friday for the continued development and this stream. Definitely again in a week's time. Until then, later.